Hi everyone, so today what we're doing is indicators. Our syllabus outcome is conduct an investigation to demonstrate the preparation and use of indicators as illustrators of the characteristics and properties of acids and bases and their reversible reactions. So, revision from last lesson, Arrhenius acids, they dissociate to form H plus and bases dissociate to form OH minus. Our Bronsted-Lowry acids donate a proton and Bronsted-Lowry bases accept a proton. Common acids include hydrochloric acid, sulfuric acid, acetic acid. Common bases include sodium hydroxide, sodium carbonate, and ammonia. So, how can we tell acidic and basic solutions apart? Well, the answer is indicators. Okay, now you've probably seen this rainbow spread before with indicators because, universal indicator. Remember that red's acidic, purple's basic, green's neutral. Okay, so what are they? They're intensely colored compounds that change color in acidic, basic, and neutral conditions. The point where the color changes is called the endpoint, and it largely depends on the pH of the solution and the indicator itself. Indicators act as Bronsted-Lowry bases, and it's that acting as an acid or a base that actually allows it to change color. When a proton is removed or added to an indicator molecule, it changes the color. So for example, indicator with a H plus on it is red, hydroxide comes along, increases the pH, removes that hydrogen, and our indicator without the H plus is now blue, and we've got water as the byproduct. pH, I have mentioned that a little bit before, but we'll go into detail in future lessons. But it's a scale used to measure the acidity or basicity of a solution. We measure it between 0 and 14, though technically we can go outside that, but it's very, very rare. pH of 7 is neutral. It's neither basic nor acidic. And this is what our pH scale looks like when we're using universal indicator. Okay, so pH of 0, very acidic, is red. pH of 7, neutral, is green. pH of 14, very basic, is purple. With our universal indicator, it changes color over the whole spectrum of pH. Now, the way it does that, it's not a single compound. It is a mixture of a whole bunch of different indicators that change color depending on the pH. Okay, we can't really use it in quantitative analysis, but we can use it for qualitative analysis. We can say that it's a 6, 7-ish, so it's close to neutral, or it's looking a bit basic or a bit acidic. Okay, and as I said before, that universal indicator is what gives us the color of that scale that I've got down there. But we have some different indicators. Methyl red. So methyl red's an indicator that's useful for differentiating between strong and weak acids. Okay, it's red below a pH of 4.4 and yellow above a pH of 6.2 with a gradual change in between them. Okay, so you can see here 0 to 3 I've got as red, 4 it starts to yellow off, 5 it's still a bit orange, but by the time we hit 6 it's got that nice yellow color, and you can see the picture up in the top corner there. Methyl orange, very similar. It's red to yellow. However, the endpoint is a little bit higher. Okay, so it's red below a pH of 3.1 and yellow above a pH of 4.4. So you can see that change is a lot tighter. Okay. And so it's not as useful for differentiating between the strong and weak acids, but it's still quite useful. We have bromothymol blue. You can see that diagram up in the top corner, how gradually it does change from 6.4 to 8.1. Okay, so it's not a very sudden change like some others, but it does change rather quickly. It's very useful for telling the difference between acids and bases. Okay, So you very rarely will you get an acid above pH of 5 or a base below pH of 8 or 9. And so it can tell us quite easily the difference. And so we can see it there. So it's yellow up to 5, then it's a little bit green around 6 to 7. 7 we start to get that darker blue color, and above 8 it gets that nice bright blue. Phenolphthalein, this is a very useful indicator for differentiating between strong and weak bases. Sorry, they should say strong and weak bases. It's colorless below a pH of 8.3. It's a very strong magenta, so very hot pink above 9.5. Now, phenolphthalein has a few little issues. The first is that above pH of 13, it does fade back to either light pink or colorless, depending on how strong above it is. And if you put into like super strong sulfuric acid, it can actually form a red color at around pH of 0. Okay, but we mostly use phenolphthalein between that 5 to 11 range. Okay, so those problems don't actually come into it all that often. Okay, so a summary. Indicators are intensely colored compounds that change color depending on the pH. The pH at which the color of the indicator changes is called the end point. Indicators include universal indicator, methyl red, bromothymol blue, and phenolphthalein, although there are many more. As for what we're doing after that, we're going to be doing a prac. Okay, so what we're going to do is we're going to make our own indicator from red cabbage leaves. The shredded red cabbage will be boiled in water to extract a natural indicator. The indicator will then be tested in a range of solutions at different pH values. Now, the method is in your booklet. It'll be under whatever lesson this is. This is a basic diagram. Those colors are not representative of what we're actually going to get, but basically what we're going to do, cut up that red cabbage, boil it, and add it to some buffers. I'll put this up on the screen when we actually do it, just so you can have a handy kind of image of what we're actually going to be doing for the prac. Okay, and so yeah, we'll do that prac, and that's all for today.